chapter from Bhuvan's copy, or if you really are interested, I can take photocopies of the pages and send you later. The point is, this expression is derived in chapter 3 of Lord's book, which you may have already seen in connection with the quantum theory of interaction of radiation with matter. So I shall just skip this part and go to the last part of today's talk, which is quantum yield. Yeah, quantum yield. So what is quantum yield? If you go to the bottom of this page, you will find what is quantum yield. This is number of emitted photons by number of atoms initiated at the upper stage. Okay, this is how quantum yield is defined. Quantum yield important because I will not give you the calculations. This is left as an exercise for you. Actually, in law, this is presented. I leave it actually equal to tau by tau sp. Now, what is tau and what is tau sp? If you scroll up, just a few lines, here. Here it is said that if you excite a system and some before exciting radiation, say when is cut off, the energy or pumping cut off, you are left with certain number of upper energy level. These atoms undergo transitions to lower levels. Okay, the transition to lower levels can replace spontaneous emission of photons via non-radiative mechanisms. So dn2 dt is equal to minus n2 by tau equal to minus n2 into 1 by tau sp plus 1 by tau nr. Tau sp is the mean life for spontaneous emission of photons, and tau for non-radiative transitions. So if you have two different ways of decay with lifetimes equal to say tau 1 and tau 2, then the effective lifetime is given by 1 by tau equal to 1 by tau 1 plus 1 by tau 2. This is true also in radioactivity. If a radioactive nucleus can decay to its daughters in two different ways, then the mean life is given by the same formula, 1 by tau equal to 1 by tau 1 plus 1 by tau 2. As an example, sodium-22, which is a radioactive nucleus, can decay by emission of a beta minus particle, that is an electron, or it can decay by emitting a positron, a beta sodium-22 nucleus either decays by electron emission or another sodium-22 decay by positron emission. So there are certain probabilities for decay by electron emission and by positron emission. The ratio of the number of nuclei decaying by electron emission to the number decaying by positron emission is called the branching ratio. So here is also an example where the atoms in the upper level can jump down to lower level mechanisms either by spontaneous emission of radiation or by a non-radiative mechanism. And if you solve equation 6.62, you immediately arrive at equation 6.63, which is how many atoms are a certain time. Okay, if V is the volume of the material, the power emitted by spontaneous emission at time t is Pt equal to, now see, the power emitted is firstly the energy of each photon, which is h cut omega 21, then the number of photons decaying per unit time per unit volume, which is dn to dt, and then you have the volume v. What is d to dt is equal to minus n2 tau if decay is by either method. But if decay is by spontaneous emission, then dn to dt spontaneous is equal to minus n2 by tau sp. So we are looking for emission of photons, so we look for spontaneous, that is n2 by tau sp. So in this formula you have n2 by tau sp, which is dn to dt spontaneous, times energy of each photon, which is h cut omega 21, times the volume v. So you can easily arrive at the right hand side of equation 6.64, which writes n to t as n to 0 exponential minus t by tau. Okay, fine. Now, finally, you have 6.65, which gives you the quantum yield. So you have to find out number of emitted photons from time t equal to 0 to time infinity. We assume that the exciting radiation is withdrawn at time t equal to 0. So the initial population in the upper level is n to 0. Okay, and final population is 0 because all the atoms will ultimately decay to the lower energy level. So how many photons are emitted? Because the decay can be either by spontaneous emission or by non-radiative means. So you have to find out how many photons are emitted. Number of atoms initially present in the upper state is of course n to 0 per unit volume. So all you have to do is find the number of emitted photons. Okay, this is easy to find because all you have to do is note that number of emitted photons in time dt is given by dn to dt spontaneous into dt, that is n to t by tau sp into dt. So you have to integrate n to t by tau sp into dt from time t equal to 0 to infinity. If you do that, you will find that phi will come out to be equal to tau by tau sp. Because tau is less than or equal to 0, and you find tau sp, then you can find out tau. And if you find out tau, you can find out tau nr. So the importance of this expression is this from the experimental point of view, that finding out phi and tau sp will give you the value of tau nr, the mean life for non-radiative transition. Now you can generalize this to a three-level system, and where you find out the corresponding quantity for the uppermost level, that is level 3. So this is also given in Lord's book, but I will not go into that. So we shall stop at this point today. Okay, right, Surendra?
Yes, sir.
Okay,
Okay, sir.
okay. Kaivallo, Bhavani, Shivshant.
Yes, sir.
Stopping at this point today,
Yes,
right?
sir.